Auzubillahiminash-shaytanir-rajeem. Bismillahir-rahmanir-rahim. Assalamu alaikum class, how are you? Alhamdulillah, I am fine and hope that you will be fine too. And taking or observing the SOPs in this COVID situation. In the last video lectures, we have discussed numericals and some of the antenna properties, including the linear and uniform linear array. Today, we will discuss or move further. And the first topic of today's lecture is the isotropic radiator. Isotropic radiator is defined as the radiator that has EM energy in all directions. That means an antenna which radiates equally electromagnetic energy in all directions is called isotropic radiator. And there is another classification that is non-isotropic. That means a radiator which does not radiate energy in all direction, or it radiate energy in a specific direction, that is called non-isotropic. And as it has been observed in the definition of isotropic radiator, and that is true that isotropic radiator does not exist. They are only referred for the uh, ideal situations or for the ideal antenna, or for the calculation of or the comparison of the actual antenna in order to uh, in order to compare the properties or the radiation patterns with reference to the isotropic radiator, that how much it has been far from the ideal radiators. The general formula for normalized electric field for non-isotropic radiator of two elements is sine phi cos psi by 2. That is the electric field, normalized electric field for non-isotropic radiators, two elements. The next is the expression of pattern multiplication. Expression for pattern multiplication. What is pattern multiplication? Basically, if we are combining more than one radiators or antennas or array antennas, so what happened? The antennas that are combining to make a single antenna, their patterns or the radiation patterns also multiply with each other, and the expression for these multiplication is discussed further. Electric field of identical radiator of non-isotropic radiator pattern multiplication. That is the formula for the non-isotropic radiator pattern multiplication for electric field is F theta phi F theta phi multiplied by Fp theta phi plus Fp theta phi. Here we will see that this F is small, this F is capital, this Fp is small, and this Fp is capital. Small f theta phi is called element field pattern. Small fp theta phi is called element phase pattern. That both of the patterns, that is field pattern and phase pattern, are combined or multiplied with other antenna that has been coupled with the first antenna, and the capital F theta phi is called array factor of isotropic element, And capital FP theta phi is called phase pattern of array of isotropic element. So here the multiplication expression for pattern of isotropic radiator is defined as E, in which both of the pattern, that is phase pattern plus the field pattern, add up together for the same antenna and then multiplied with the other antenna. Next is the binomial array. Binomial array is basically a type of array which works on the principle of binomial series, a very well known mathematical algebraic series used to express a binomial sequence or binomial series. Works on the principle of binomial series, binomial array, work on the principle of binomial series. Elements are excited according to current levels, determine the binomial coefficient, that is NCR. These are all the terms that are used in binomial series. And basically that array works on these principles. So the terms that have been used in the binomial series are working as the elements here. Elements are excited, that is elements are fed according to current level determined by binomial coefficient, that is NCR. Here n are the number of elements. No side loops has been created, that is the basic advantage of this binomial array antenna. But beam width is large, which is undesirable, which is not suited for the point to point communication. Directivity is small, that is another disadvantage of this antenna. And high excitation levels that are required for central element of large arrays. That means if we have to use the binomial array as an antenna, we have to provide higher excitation levels to the center elements of the array antenna as compared to the side elements. That is also a disadvantage of this type of antenna. Following is the figure which provides the excitation levels according to the number of elements. That is, two, if we have element binomial array, negative amplitude will be 1 1. If we have 3, we have to provide at the center the maximum level of excitation, that is 2. For 4, again in the center elements, we have to provide more excitation levels here also. And in the as if we have an binomial array antenna which contains 9 elements, you can see that the excitation level is so high, that is 28, 56, 70. This is a very high number, and that is basically the major disadvantage of this antenna. These excitation levels are defined from the Pascal triangle, that is the mathematician Pascal's Eventon, which has proved this triangle as the uh, power of mathematics. This Pascal triangle provides the excitation level for binomial array. And here we can see it has been started from the 1, That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 4, 6, 8, 9 ones, and here are 8 ones. 1, 2, 3, 4, 5, 6, 7, 8. So the center is big, that is 2, then 3, then 4, 6, 4, then 5, 10, 10, 5, then 6, 15, 20, 15, 6, 7, 21, 35, 35, 21, 7, then 8, 28, 56, 70, 56, 28, 8. How it works? It works as this: 1 plus 2 is 3, 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 1 is 6, 6 plus 1 is 7, 7 plus 1 is 8. It contains 8 rows. In this one also, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 1 is 6, 1 is 7, and 7 plus 1 is 8. Then 6 plus 3, 9 is 1 is 10. 10 plus 4 plus 1 is 15. 15, 5, 20 is 121. 21, 6 is 27, 1 is 28. It is also like this. And this one, 20, 10, 30, plus 4, 34, plus 1, 35. Here is 35. Then 35 plus 15 is 50. 50 plus 5 is 55, and 1 is 56. Here, 56 plus 21 is 77. Sorry, 35 plus 15 plus 5 plus 1 is 70. 35 plus 15 plus 5 plus 1 is 56. It's like this: 35, 15, 5 plus 1 is 56. Okay, it also been described as this: 1 plus 1 is 2. Okay, 3 plus 3 is 6. 10 plus 10 is 20. 35 plus 35 is 70. So that's how this Pascal triangle is being created, and from this the values of the binomial array has been taken. Now next is the method of excitation of antennas. Basically, here we will discuss how the antennas can be provided, how the antennas sources can be provided in order to start the working of the antenna, or we call it as excitation of the antenna. We have four methods: center feed, shunt feed, end feed, and tap feed. At center feed, we want to excite the antenna from the center. We have to give the source at the center of the antenna by open wire transmission line. If we are talking about the shunt feed, the shunt feed, the threading is done through solid dielectric low impedance line, that is called shunt fed. That is fed through solid dielectric low impedance line. End feed, end feed is defined as the antenna has been fed at either side with a single vertical wire. That it can be provided source at any or either side, but with a single vertical wire. That the source is being given to the antenna through a single vertical wire. Then the tap feed. Tap fed is basically defined as the horizontal antenna is tapped with a vertical wire. That means if the excited or the source as we have to provide the source to the horizontal antenna, we have to tap or connect it with a vertical wire, or if the antenna which has to be excited is vertical antenna, then we have to tap it with a horizontal wire. That is called tap fed. These are the four excitation methods of antennas. Now there is a problem arises in excitation of antenna is this, that if the impedance of the antenna with the source that has been provided the power are not matched, then the excitation of the antenna is not proper. So for this purpose, we have to match the impedances of the antenna with the source, providing different methods. We used three methods that are called, one is called stubs, number two is folded dipole, and the third is balance, that is called balance unbalanced. First we discuss stubs. What is stubs? To minimize the reactance, stubs are used to minimize the reactance component of the impedance and radiation losses. That is the purpose of the stub. How we use stub? Stub is basically have two types. One is open circuit stub and the other is short circuited stub. In open circuited stub, we will use vertical wires. Sorry, we will use transmission line, and kept it open circuit. In short circuited stub, we will use a transmission line and connect both of the ends with each other. This stub method is used to minimize the reactance and the radiation losses of the antenna. The second method is called folded dipoles, and the next one is the balance, that is balanced and unbalanced. Folded dipoles are used to increase the impedance of the antenna in order to match it with the source. The folded dipole is basically the part of the transmission line or some hard wire that has been folded as shown in the figure. It provides single fold provides the impedance of 292 ohms and the double fold provides the impedance of 675 ohms. This folded dipole is basically used to increase the impedance and is lesser used in impedance matching techniques. The third and the foremost and the most important that is being used extensively for impedance matching is called balance, that is balanced unbalanced. The abbreviation is balanced unbalanced. Broadband, it is used for broadband and narrowband antennas. It is used for broadband and narrowband antennas. Transmission lines are used for higher frequency and center tap transformers are used for lower frequency. In order to balance the impedance for higher frequency antennas, or for the broadband antennas, transmission lines are used as an impedance matching device, and center tap transformers are used for narrowband and for lower frequency devices in order to match the impedance of the source and the antenna. The next is the losses that are actually happen in between the transmission. There are a number of losses. The first one here is the actual transmission loss, that is also called Friis formula, which is the combination of which is the combination or the ratio of transmitted power over received power, and the mathematical value for actual transmission loss is tan log 4 pi d over lambda square multiplied by 1 over GT/GR. That is calculated in the dB. 4 pi d is the constant. 4 pi d over lambda is the constant. GT and GR are basically defined here as the transmission gain and receive gain, and that is the equation for actual transmission loss. For basic transmission loss, the formula is tan log tan 4 by d over lambda square. Here GT and GR are considered as equals to 1. This is the basic transmission loss in which gain is not effectively working. The next is the signal to noise ratio, which is very important in signals and transmissions. That defines the ratio of the signal to noise, that how much noise is present in the signal, or how much signal strength is being found in the transmission signal. It is the ratio of the signal and noise, which is being simplified as SA divided by TA plus TE into KB. SA is basically the input signal, TA is the antenna temperature, TA is the effective noise temperature, and here KB are in which K is the Boltzmann constant and B is the bandwidth. That defines the signal to noise ratio at standard temperature, that is 290 degree Kelvin. Next is the noise figure. Noise figure defines the noise strength regarding the temperature, or how much noise is being created from the temperature. The formula for the noise figure is 1 plus TE over T naught, that is T is the effective temperature. T is defined as the effective noise temperature, and T naught is defined as the standard temperature, that is 290 degree Kelvin. So it is basically the uh, ratio between the effective noise temperature and the standard temperature. Next is the effective temperature, that what is basically the effective temperature is. Effective temperature is basically the antenna temperature that is being uh, generated from the noise in the effective area of the antenna, and it is being calculated from the noise figure, that is T naught into Fn minus 1 is the effective noise temperature. I hope that this completes this chapter, and I've tried to make you understand as per my ability and capability, and I hope that you will understand these things softly, and we will discuss it inshallah in the Zoom session afterwards. Thank you very much, and be safe. Follow the SOPs. Thank you very much.